Hello and welcome. Today, we're diving into the world of giant machines built to explore the tiniest components of reality, particle accelerators. Think of machines like the Large Hadron Collider, or LHC, at CERN. These incredible feats of engineering speed up subatomic particles, like protons, to almost the speed of light and then smash them together. Why? To see what comes out. It's how we discovered fundamental particles like the Higgs boson and mimic conditions just after the Big Bang. But the biggest questions remain. What is dark matter? Why is there more matter than antimatter? To find answers, we need even more powerful accelerators. The LHC has been amazing, but pushing further with the same technology means building machines on an almost unimaginable scale and cost. So, what's next? Scientists and engineers are designing the next generation right now. One idea is a successor to the LHC, like the proposed Future Circular Collider, or FCC. Imagine a ring nearly 100 kilometers around, almost 4 times bigger than the LHC. It could first collide electrons and positrons for super precise measurements, then maybe graduate to even higher energy proton collisions later. China is also planning a similar, massive circular collider. The big challenge? Developing much stronger magnets to keep those super-fast particles bending around the enormous track. Another approach is linear colliders, like the proposed International Linear Collider in Japan, or the CLIC project at CERN. Instead of a ring, these are straight tracks, potentially tens of kilometers long, firing electrons and positrons directly at each other. Linear colliders are great for precision work, offering a cleaner collision environment. Here, the engineering hurdle is making the particles accelerate much faster over shorter distances to keep the machine size somewhat manageable. Then there are completely new ideas that could lead to smaller, maybe cheaper, accelerators. Plasma wakefield acceleration is super exciting. You fire a powerful laser or particle beam into plasma, basically ionized gas, creating intense electric fields, like a wake behind a boat, that can accelerate particles dramatically faster than current methods. It's still experimental, but making huge strides. Another cool concept is the muon collider. Muons are like heavy electrons, but they decay very quickly. If we could figure out how to create, control, and accelerate them fast enough before they disappear, we could potentially achieve very high energy collisions in a more compact circular machine compared to electron colliders. But capturing and accelerating muons in microseconds is a massive technical challenge. Building any of these future machines involves overcoming huge engineering problems. Better magnets, perfect vacuums, new materials, immense power, precise control, and detectors that can handle floods of data. It requires global teamwork and serious long-term funding. But the payoff could be revolutionary. These next-gen accelerators aim to measure the Higgs boson with incredible accuracy, search for new particles like those predicted by supersymmetry, hunt for dark matter candidates, understand the matter-antimatter imbalance, and maybe even discover entirely new forces of nature. We're building the tools to ask the most fundamental questions about our universe. It's a journey requiring immense creativity and collaboration, holding the key to the future of physics. Thanks for tuning in.